Hey guys, today I want to present a solution to the second number theory problem of Iran Math Olympiad 2021. At first, let's have a look on the problem statement. We are asked to find all functions f from the positive integers to the positive integers such that f to the power of a of b plus f to the power of b of a divides 2 times f of ab plus b squared minus 1 for all positive integers a and b. F to the power of a means applying f iteratively a times. So for example, f squared of x is equal to f of x. Our first step is to plug in b equals 1 into this equation, because then we see that f to the power of b of a is easy to handle, namely it's f of a, and on the right hand side we also have f of a. So let's do this, and we get that f to the power of a of 1 plus f of a divides 2 times f of a plus b squared, which is 1 minus 1. This cancels out. So we have that f to the power of a of 1 plus f of a divides 2 times f of a. And since all of these numbers here are positive integers, this directly implies that f to the power of a of 1 must be equal to f of a. It would be nice if f is injective, because then this would give us that f to the power of a minus 1 of 1 is equal to a. So let's consider this as our first case. This equation here immediately implies that also a plus 1 is equal to f to the power of a of 1, but we already know that this is equal to f of a. So f of a equals a plus 1 is our first possible solution and the only possible solution in this case. And we can easily check that this solution is a solution to our problem, and therefore we are done with this case. So let's write this down as our first solution and then consider our second case. In the second case, f is not injective, and therefore we can find two different positive integers, x and y, such that f of x is equal to f of y. Therefore, using this equation here, we directly get that also f to the power of x of 1 is equal to f to the power of y of 1. And this means that if we consider the function mapping n to f of n of 1, this function here must be eventually periodic. Since f to the power of n of 1 is equal to f of n, we also know that the function f is eventually periodic, and therefore the function f of n is bounded. So we know that there exists some positive integer m such that f of a is less than or equal to m for all positive integers a. Right now, there's no good way to use this condition here, and therefore, at first we want to figure out more information about our functional equation, and especially about the term f to the power of a of b. For this, we want to use the condition f to the power of a of 1 equals f of a again. Namely, we can write f to the power of a of b to be equal to f to the power of a minus 1 of f of b. Now, this is equal to f to the power of a plus b minus 1 of 1, and this can be written as f of a plus b minus 1. In the same way, we get that f to the power of b of a is also equal to f of a plus b minus 1, and therefore we can divide both sides of our divisibility condition by 2 to get that f of a plus b minus 1 must divide f of ab plus b squared minus 1. We see that the left-hand side of this divisibility condition here is symmetric in a and b, and therefore we can swap the variables without changing the left-hand side, and on the right-hand side we get f of ab plus a squared minus 1. And then we can subtract both of the right-hand sides to get that f of a plus b minus 1 must also divide b squared minus a squared. Plugging in b equals a plus 1, we get that f of 2a divides a plus 1 squared minus a squared, which is nothing but 2a plus 1. We are finally ready to use the condition that f is bounded from above, because now we are able to choose 2b plus 1 to be equal to a prime number p in such a way that p is greater than m. And then we get that f of 2b, which divides p, and since we choose p to be less than m, we know that f of 2b is less than p. This implies that f of 2b, which is nothing but f of p minus 1, must be equal to 1. Remember that we figured out that f to the power of a of 1 is equal to f of a. Therefore, this is equal to f to the power of p minus 1 of 1. This means that we can find an integer s such that f to the power of s of 1 is equal to 1. Therefore, we are motivated to consider the smallest such s. Hence, we know that s must divide p minus 1, and now we can use Dirichlet's theorem, which tells us that we can choose this prime number p to be congruent to minus 1 modulo s. So let's write this down. Taking this prime number p congruent to minus 1 modulo s, we directly get that s must divide minus 2. This means that s is either 1 or 2. For s equals 1, we get that f of 1 is equal to 1, and therefore we have that f of a, which is equal to f to the power of a of 1, is equal to 1. So f of a equals 1 for all positive integers a is the only solution in this case, which is also easily checked to be a solution. So we can write this down as another solution. For the case that s is equal to 2, we at first get that f of a equals 1 for a even, and otherwise f of a is equal to f of 1. To evaluate the value of f of 1, we plug in a equals b equals 2 into this equation here to get that f of 3 divides f of 4 plus 2 squared, which is 4 minus 1. Here f of 3 is equal to f of 1, and since 4 is even, we know that f of 4 is equal to 1, and therefore the right hand side is equal to 4. So f of 1 must divide 4. Since s was chosen to be minimal with the condition that f to the power of s of 1 is equal to 1, we know that f of 1 can't be equal to 1. And therefore, we conclude that f of 1 is either 2 or f of 1 is equal to 4. So we have two more possible solutions. You can check on your own that our last two solutions also satisfy the given condition. And therefore, we figured out all of the solutions and we are done.